Okay, so now we're going to be discussing about mesh analysis. Now, nodal analysis, as we've seen previously, was based on KCL, and it allowed us to write current equations in terms of voltage. Now, the advantage of doing so is that we're able to solve for the voltage very quickly without ever needing to set up KVL and KCL together to create multiple systems of equations, because this can get really confusing. So using KCL, we would define we would find the following. First, we need essential nodes. And recall that essential nodes just means that it has three or more branches going in or out of it. We need a reference, or what we call ground. To kind of circle it might get a little misleading, but just in case you do see it, we're always talking about ground. And ground means a place where there's no voltage, ideally, 0 volts. We also have problem. Now, the problem is not up to you to assign. It's been given either by the book or by any homework, right? This one you ignore until the end. Ignore until the end. The end. And by the end, I mean like when you set up the equation. Then, from here, you also have the current directions. Sometimes the book may assign current directions to you. You can't change that. But if it's not touched on, you assign the current direction. Then lastly, you'll set up current equations. And that was okay for the most part. But equivalently, there is another method based on KVL that allows us to set up voltage equations in terms of current. So we have mesh analysis. There's a few kind of rules to this, but the main rule is simple nodes, simple loops first. We call these loops mesh loops. And then super loops are only kind of necessary in order to bypass dependent sources. Unfortunately, they'll not be addressed in the scope of this review, but it is important to review it. We have simple loops. We have to assign polarity. Assign polarity if not given. Similar to nodal analysis, if the book or any homework problem gives you a polarity or current direction already, you do not mess with it. Similar to nodal, ignore question for now. Lastly, we set up voltage equations. Set up voltage equations in terms of current. So let us use a similar problem example that we have used last time. So this is 7 volts. This is maybe, I don't know, 2 ohms, 6 ohms, 5 ohms. Now, the assignment of values is arbitrary. We don't necessarily want to worry about it too much. And let's suppose that I ask, what is the current going into this node I? So let us suppose we first ignore this question and we draw our mesh loops. Just like just like us assigning current direction, us doing the direction of assignment for mesh loops is arbitrary. So we have I1 here and I2 here. So first, we have our loops. Then we need to assign polarity. However you feel is your assignment of polarity is up to you. And just like current direction, it is arbitrary unless it's assigned. Okay, so now from here, we write KVL equations. So first, we have, in this case, rise, drop, drop. So we have over here 7 volts equals to I1 times 2 ohms plus I1 times 6 ohms. Or rather, I should say, plus 6 ohms times I1 and actually minus I2. Okay, so in this situation, current I1 sees positive first, so it's going to be positive. But current I2 sees negative first, so it's going to see negative. And so it leads us to this 6 ohms times I1 minus I2. Okay, and that's for one loop. Now, the second loop, we have, in this case, rise, drop, drop. So in this situation, we have 6 ohms times I1 minus I2 equal to 5 ohms times I2 plus 10 volts. And that's our second mesh equation. Now, in this situation, we're asked about the current I1. So we actually follow the direction of I. It's equal to I2 minus I1. So in this situation, we need both I1 and I2 in order to figure out our currents, or in order to figure out their current value, I. So, as usual, we solve it just like we would for nodal analysis. However, notice that solving systems of equations gets a little complicated. So we're actually going to employ something clever. We're going to use Cramer's method. So Cramer's method is a type of linear algebra method in order to quickly solve systems of equations by basically generally solving using determinants. So first, we have, in this case, something like so. So we have 6, and then we have over here 6 times I2 minus I5, so we have 11 I2 equal to 10 volts. From here, here's how we use Cramer's method. Cramer's method involves finding the determinant of the following. So what is this equal to? Well, first, triangle 1 means take all the values relating to I1, replace it with the right-hand side. So we have 7, 10, and then we keep the rest. Divide this all over the determinant of the left-hand side, which is just 8, negative 6, 6, negative 11. So once we do that, to find the determinant, write We do diagonal, anything we multiply to the diagonal right is positive, anything to the diagonal left is negative. So we have negative 77 plus minus 660, or just plus 60, divided all over 8 times negative 11 minus 36. So we have 88, negative 88, plus 36. And we can simplify this as negative 17 divided by 52, or just 17 over 52. Okay, amps. Similar situation here. I2 is going to be defined as, so now because we are looking at the I2, we ignore everything on the left hand side pertaining to I2, replace it with the right hand side. So we have 8, 6, -6, -11. Oh, sorry. No, you need 7 and 10. And then the bottom remains the same, like so. So now we do the determinant once more, and we get the following results. So in this case, it's going to be 38 divided by negative 52, or 17 over 26 amps. With this knowledge, we have I now being equal to I2 minus I1, or 17 over 26 minus 17 over 52. Now this one is just the same as negative, and then we have 38 plus 17 divided by 52. We have, in this case, 58, so we have 55 divided by 52, or negative 55 over 52, roughly about 1 amp, negative 1 amp. And so that becomes our becomes how we use mesh equations. Actually, within this, what you might observe is that anytime you actually have multiple systems of equations dealing with mesh currents, as they're called, you can always use Cramer's method. But the caveat is that Cramer's method is best solvable whenever you pertain to using it to solve 2x2 systems. When it comes to 3x3 systems, there is a method to quickly do it, but it is complicated. And then 4x4, you have to do a lot more work. So whenever you can, usually in circuit analysis, whenever you're faced with 3x3 systems or 4x4 systems, that indicates there should be a way to solve it quickly, to reduce it down to a 2x2 system. So in this case, this is just a simple example, and this is just for us to kind of get familiar with nodal and mesh analysis. Okay, that has been the end of the shortcuts. So thank you.